Okay, we're on question 5, and 5.1 says, in the diagram below, P is the point 12 and 5. And then we have T is A and B, and they tell us that OT is perpendicular to OP. As we can see, we have a 90-degree angle there. And they also tell us that PS is perpendicular to the x-axis. Okay, also a right angle triangle over there. And POS, angle POS is equal to theta. And the questions are, the first question is, without using a calculator, determine the value of tan theta. Okay, so let's go ahead and start with that one. So with 5.1.1, tan theta, we're really just looking at this diagram. So do you see that we don't really need, since we know the tan, right? Remember tan using SOHCAHTOA, the TOA part is for tan, which is opposite over adjacent. So you don't even need the hypotenuse for this. So don't go ahead and start finding it now. You don't need it here. So we're going to go ahead and say the opposite side. Let's go ahead and see what exactly that would be. Here's theta. The opposite side is this. Now, what exactly is this in our coordinates of P? As you can see, this is a vertical line, meaning it's telling you what exactly your y value is. So the y value is 5. And then the x value, okay, that's your adjacent side. That is 12 because you're going to go 12 and then 5 up to get the point P. So since we have that, the opposite side is 5 and the adjacent side is 12. So there we go. That's our answer for the first question. And the next question, 5.1.2 says, we need to find sine theta. Now we need the hypotenuse. So we're going to have to use Pythagoras since we have a right angled triangle. So we're finding OP. So we can say OP squared. So let me just say 5.1.2. OP squared equals, and we're going to take the shorter side squared plus the other shorter side squared. So that's 5 squared plus 12 squared. And then we're just going to find the square root of this. So what exactly is that going to give us? OP would be the square root of all of that. Let's just find that on our calculator. And we get 13. So that is equal to 13 finally, right? So now that we know the hypotenuse is 13, we can actually find sine. Sine is SOHCAHTOA, is the saw part, which is the opposite side over the hypotenuse. So opposite over hypotenuse, which is going to be, our opposite side is 5 over hypotenuse, which is 13 as we see there. And that will be our answer for that. Okay, moving on to the next question. So let me actually just tell them that sine theta equals 5 over 13. So we'll get our full 2 marks. The next question is 5.1.3, which says you need to, without using a calculator, determine the value of A if TO is equal to 19.5 units. So TO is 19.5 units. And you need to find exactly what the value of A is. Okay, so this type of question has shown up a few times. So what we're going to do here is we are going to use the theta and the fact that they gave us 90 degrees over here. Because they're speaking about T, which is in the second quadrant, we can go ahead and drop a vertical line down. And we know we're referring to this triangle over here. But what's the reference angle that we're using? Well, you notice how in these diagrams, right, you always have the angle being drawn from the x-axis to the line, okay, to that radius or that terminal arm. It's always been drawn like that. Well, that's the angle that we have expressed here. What happens is you can, using your reductions, reduce the size of that angle so that it becomes an acute angle. Okay, so we really just need to find what exactly the size of this angle is. The size of the angle that OT forms an angle that is made up of the theta and the 90 degrees, which if you calculate is really 90 degrees plus theta altogether, theta and 90 degrees. So that's our reference angle over there. So we can go ahead and use that angle and we're going to use it to find A. But we need to do this in a way that is actually going to help us to quickly find A. So let's figure out where A is in our diagram. A, as you can see, is your x value. So your x value is going to be here, just like you see, this was the x value 12, right? Because we have to go 12 units to the right, then 5 units up. So that is our x value over here. That's A. And then B is our y value because that's the height. That's y. So B over there. So in order to find A, do you see that A is your adjacent side, ironically? Okay, it's not because it's A, it's just because it is the actual adjacent side. Since your angle, your reference angle is this side, then your adjacent side is here. B is the opposite. Since they gave us 19.5, let's try to focus on using that hypotenuse and only the A. So if you're using an adjacent side and a hypotenuse, what function are you going to use for that? The function with A and H, adjacent and hypotenuse, would be cos. So katoa, okay? Cos. So let's go ahead and use cos here. So with 5.1.3, what we're going to say is we're going to find cos of this angle 90 degrees plus theta. So cos 90 degrees plus theta, and find out what exactly that is equal to. So cos 90 degrees plus theta is equal to our adjacent over hypotenuse. Okay, we have to use what they asked us to find and what they gave us. So that's A over 19.5. That's A over 19.5. But here's where we use some of these trigonometry rules that we know. So when you look at this, cos 90 degrees plus theta, what does that look like to you? That is cofunctions. So if you look at cofunctions, which I'm putting on the screen right now, right? The cos 90 degrees plus theta, that will give you negative sine theta. And you see how it gets reduced to theta again. So negative sine theta is equal to A over 19.5. And now we just need to solve for A. Okay, so to find the value of A, well, we already know what sine theta is. In relation to the diagram that we have here, this was in terms of theta. We knew what sine theta was. Sine theta is 5 over 13. So negative sine theta is negative 5 over 13. See, we're using the other diagram to help us solve for this diagram because it was in terms of theta. So this is equal to, and we can go ahead and say, well, let me write it like this. Negative 5 over 13 is equal to A over 19.5. My A always looks like a 9. Okay, so there. Now we just need to solve for A. As you can see, since A is over here, instead of cross multiplying, because then you're going to have to divide, you can just get rid of that denominator of 19.5. Since we're dividing by 19.5 to get rid of it, you multiply by 19.5 on both sides. So really just saying that that cancels and you have A alone is equal to, and if you say 19.5 multiplied by negative 5 over 13, you would get your answer. So let's go ahead and do that. And that gives us, well, you can put it as a fraction if you want, but as a decimal, it gives us negative 7.5. And that is our value for A. Okay, moving on to the next set of questions. The next question, 5.2, says, determine the value of the following without using a calculator. So we have a trig expression and we have to simplify it. Always just make sure you simplify everything that you can, okay? If something is too big, you reduce it. If there's a negative angle, add 360 degrees to it. If there are cofunctions, use your cofunctions. And the main thing is be careful when simplifying, to simplify carefully and not quickly so that you don't make little mistakes. Okay, so what we have here, we have sine 360 minus x, just like sine 360 minus theta. That is in cos's quadrant. It's supposed to be in cos's quadrant and sine is negative here. So that would become negative sine of our angle there, which is 2x. Then we have multiplied by sine of negative x. So I'm going to actually simplify on screen just to show you what happens. You see that we have negative x. X represents your angle, which means your angle is negative. When your angle is negative, you need to add 360 degrees. And so what really happens is that becomes sine 360 degrees minus x. And if you simplify this, it becomes, because it's in cos's quadrant and sine is negative there, it becomes negative sine x. Okay, all over. And over there, you see that you have cofunctions. Remember your cofunctions? Okay, so that simplifies to positive cos x. Then we continue plus, and we have 2 cos squared of 180 degrees plus x. Now, regardless of whether the cos 180 degrees plus x becomes positive or negative, it still gets squared because we have squared over there. So the reason I'm saying that is because if you simplify that, you see that that is actually tan's quadrant, that 180 degrees plus theta, right? So you know that that's supposed to become negative cos x. But then it gets squared. So it becomes positive afterwards. So that is 2 cos squared x. Okay, so this is what we have now. And we're just trying to simplify. Okay, so first and foremost, we see x, and then there's a 2x. So clearly that needs to go. That needs to change. What can we do with sine or negative sine 2x? Well, first of all, these two are multiplying and they're both negative. So they're going to, the negatives will become positive. So the negatives are gone. And when we go ahead and simplify that, that is double angles. And we only have one expansion for that, which is 2 sine x cos x. And then we multiply that by sine x. And this goes all over cos x. Convenient, okay? You see that those will cancel. And we have plus 2 cos squared x. And this is equal to our coses, cos x and cos x cancel because we are multiplying all through. If there was an addition sign here, you can't cancel that cos x. Okay, so then we have that. And this is now 2 sine x times sine x is sine squared x. And there's no denominator now. Plus 2 cos squared x. And as you can see, this looks like the identity for sine squared x plus cos squared x being equal to 1. So the only thing here that we need to take out is the common factor of 2. So take out 2 as a common factor and we have sine squared x plus cos squared x. And we know that they give us 1, like the identity. So this is equal to 2 times 1, which is equal to 2. And that is our answer. Okay, so that was quite simple. Just make sure you practice a lot of these grade 12s, and the memo is there. You can use the memo. Just ensure that you are practicing first before looking at the memo, because if you keep looking at the memo and you keep seeing the answer, it doesn't actually help you get there. The thing about maths is that you have to kind of struggle to get to that answer. Okay, so you just keep pushing. Okay, moving on to the next question. And we move on to 5.3. And 5.3 says cos 42 degrees is equal to the square root of k. So without using a calculator, determine the value of sine squared 69 degrees in terms of k. Okay, since they told us cos 42 degrees is equal to k, and we now need to express this in terms of k, then we need to find a way to make that angle 69 degrees, right? To get it to look like 42 degrees, to get it to actually be 42 degrees in some way, or really just get it to relate to 42 degrees. Now, the angle that we have is already acute, so we can't even reduce it. So since reduction does not work, what we can just decide to use is cofunctions, okay? Because it's another form of somewhat reducing an angle, okay? We can try using cofunctions. So I'm going to go with cofunctions because I can't really reduce 69. So let's start off. We're saying sine squared 69 degrees. And let us go ahead and use cofunctions. So we're going to say sine squared of 90 degrees minus what gives you 69 degrees. So if you say 90 degrees minus 21 degrees, okay? And then you can apply the cofunctions to this. So this, just like in our cofunctions, right? Since sine 90 minus a is equal to positive cos a, we're going to go ahead and say this is equal to cos squared of 21 degrees. Now, I don't have to consider that it's squared because the thing is that if you find sine 90 minus 21, it becomes positive cos 21. So I don't have to really just overthink this squared because it's not going to become a negative either ways. Okay, so we have cos squared 21 degrees. And now what can we actually do with this? So we're still trying to focus on how can we get this to relate to 42 degrees? Well, 21 and 42, they do actually relate with each other. Do you see that 21 degrees is exactly half of 42 degrees? So that means we're probably using double angles. So this is half the angle. You know, with your double angle formulas, as you can see them here, right? We have, since these are speaking about cos, right? Cos 42, and we have cos squared of 21 degrees, which is half of 42 degrees. We know that we're going to be using the cos 2a formula. So what I'm looking at this as is the 21 degrees, because it's half of 42 degrees, that's going to stand for your A. Okay, your A is the 21 degrees, and then the 2A is double 21, which is 42. Okay, so this is how we can use this. So we're going to use the cos formula, that one, the cos 2a, the double angle formula for that, which is cos 2a equals, and we can use the one with the cos squared, since we have a cos squared of a, okay, half that angle. So we can use this one, which says 2 cos squared a minus 1. And this is going to be equal to, we have cos of 2a here. So that is 2 times, we know a is 21 degrees, which is, if you simplify, is really just 42 degrees. So cos 42 degrees is equal to 2 times cos squared of 21 degrees, which is our a, and then minus 1. Now, remember what we're trying to solve for. We're trying to express this, the value of this, in terms of k. You already know that sine squared 69 degrees, that's what is equal to cos squared 21. So you just have to make this the subject, cos squared 21 the subject, and by doing that, you would have found sine squared 69, since it was equal to that. So let's go ahead and make that the subject. Okay, because it's already positive here, I'll leave it here and leave this as cos 2 cos squared 21 degrees, but I'll take that negative 1 over. But here, remember, it needs to be in terms of a. We have a cos 42 degrees here, and they told us that cos 42 degrees is equal to the square root of k. So that's the square root of k, which is equal to this. And we're taking this negative 1 over and becomes a positive 1. Okay, remember, we're just trying to solve for the cos squared 21, because that is equal to sine squared 69. So we're going to have to get rid of the 2 by dividing both hand sides by 2. And so this means that cos squared of 21 degrees is finally equal to the square root of k plus 1 all over 2. And that is our answer. Okay, that is for 3 marks. And we move on to the next question. Okay, we're on question 5.4, and it says, given the identity, and we have sine 5x cos 3x minus cos 5x, and then all of that over tan 2x minus 1 is equal to negative 2 sine squared x. And we need to prove the identity. So already from looking at this, you can see the left-hand side has more detail than the right-hand side. We can actually expand it and simplify it further and get it to this point. So we're going to go ahead and start with the left-hand side. So we'll just say left-hand side equals and rewrite what we have on the left. And now that we have this, we can go ahead and start simplifying. So I want you to notice something about this. Do you see that we have sine, cos, sine, right? And then we have 5x, 3x, 5x, 3x. That is the order of compound angles. So that is the compound angle for sine, the one with a minus. Just like we have that in the form of sine A, cos B, and minus cos A, sine B, okay? Because you see, the A is consistent. It's both 5x and the B is consistent. That can get reduced to sine of, just like the way that gets reduced, it gets reduced to sine 5x, and we have minus 3x, okay? Sine A minus B. That's what it gets reduced to. And we have over. Now I'm already looking at tan, and tan can be changed to sine over cos. So let's just change that. Because this is one fraction on its own, I'll just give it a bracket. So put it together. And we know that this is being divided by tan 2x, which is really sine 2x over cos 2x, right? 2x. And then we have minus 1. Okay, so we'll apply that later. So this gets reduced to 5x minus 3x is 2x. So that's sine 2x. Divided by, but because we're dividing by a fraction, you can tip and times. So you tip by swapping the numerator and denominator of that sign, right? And then you change your division to a multiplication sign. So we have that, and we have minus 1, of course. Now, when we have this, do you see that we can actually cancel the sine to x diagonally? They would cancel. And so you're left with only cos 2x minus 1. Let's just look at what we need to get it to be. We need to get it to be negative 2 sine squared x. And the first thing I already noticed is, first of all, that is sine and there's no 1. So the fact that it's already sine, you know that you have to change that cos 2x to one of the expansions of cos 2x, right? But that has a sign. And that one would be the 1 minus 2 sine squared x. And then we still have minus 1. So what happens here is your positive 1 would subtract with your negative 1 and become 0. And you're just left with the negative 2 sine squared x. And that is equal to your right hand side. And we have proven the identity. The left hand side is therefore equal to the right hand side. Okay, moving on to the next question that comes after this one. Okay, so it's like general solutions, and then we're just going to actually find the specific solutions. So you're going to treat this as your reference angle, and I'm going to try and use this as a way to correct a mistake that I made in that general solutions video I made when I spoke about the easy method, the quick method, and the standard method that we work with. Let's say we had tan of theta was equal to negative root 3, right? And so you were trying to solve for theta, like the general solution. So we would say our reference angle is equal to, now I don't consider the, quadrants, okay, because that is the standard method that we work with, but I was working through it using the quick method. I just want you guys to remember this. With this one, when we take tan over and we find shift tan of negative 3, which is going to be negative 60 degrees, shift tan negative square root 3, sorry, right? It's negative 60 degrees. So we're going to use that angle like that. Once we find our solutions, remember for tan, it's very simple. You don't have to overthink this. You just say theta is equal to whatever that was, and then you say plus k of 180 degrees. If you want to make the angle positive so that the answer looks like the answer you would have gotten if you used your quadrants, the standard method, right? Make sure you add 180 degrees to make it positive. The reason why is because the tan graph repeats itself every 180 degrees, okay? It has a cycle of 180 degrees. So if you want to get that to become positive, you have to add 180, not 360. I know I said 360 there. I was a bit tired. I was already working on the paper 2 of May to June 2024, and I had to edit it that same night, so I didn't see that mistake. I apologize for that. Okay, so we're going to work on this. We just need to make tan of 2x be equal to 0. Okay, so tan 2x being equal to 0, let's solve. So just like we worked on that other one, we're going to find the reference angle. So say reference angle is equal to shift tan, of course you won't include this, it's not necessary, of 0. Okay, now tan 0 is still 0 degrees, doesn't really change. So our reference angle is 0 degrees. So now that we're solving for x, we're going to take this value here, okay, that was in front of tan. You're going to take that and say 2x is equal to, and we are going to take our reference angle, and then you're just going to say plus k of 180 degrees. And done. That's the quick method, right? So we're just saying it's 0 degrees plus k 180 degrees. And as you can see, once you divide both sides by 2 to solve for x, and then when we divide both sides by 2, we get x here is equal to 0 divided by 2 is 0 divided by 2 is 0 degrees. And then k 180 divided by 2. 180 divided by 2 is 90. So that is k 90 degrees. Okay, so remember that you need to solve for this interval. Okay, you need to solve for x within that interval. Remember, k is an element of integers. So it's not a big interval, so it won't take that long to solve really. You're just going to go ahead and substitute values for k and see which ones work. So we can actually solve for x here. Because it's just 0 plus k 90 degrees, it can't really go much places. You can decide to substitute in place of k, you could substitute 0, okay? And if you substitute 0, because we need to substitute only integers, you see that the x value you're going to get there is 0 degrees, and then 0 times 90 is 0. So that's 0 plus 0. So you get 0. And we know that 0 is within that interval. And then if you put anything other than 0, it's really not going to work. It's just going to be either too big or too small. So if you try, for example, -1, -1 times 90 is -90. 0 plus -90 is still -90. That is way beyond the interval. It's too small. And if you tried +1, that's going to be +90. 0 plus 90 is 90. That's also above. So in this case, right, that's all that works if you make tan equal to 0. But here's what we need to consider. They want us to tell them the value of x for which the identity is going to be undefined. And the reason why I'm doing this is because we're specifically using the function tan. You see, the tan graph has something that sine and cos graphs don't have. It has asymptotes. And those asymptotes, at those places that it has asymptotes, the graph is actually, well, if you found the equation of it, for those x values, it's undefined. Okay, so because it doesn't have a y value at those points. Okay, so, and you just need to remember where exactly this happens. So remember, we have tan 2x here, right? But the normal tan graph, the y equals tan theta, where does it have an asymptote? And we don't have to overthink this just because the interval that we're using is really small. So I'll just use a tan graph that goes from 0 to 180 degrees. I will not be too extra with this. Where this has an asymptote is at 90 degrees. It has here, okay? If you find tan 90, it's going to say error on your calculator because there is an asymptote at that point. So tan of 90 degrees, complex infinity, okay? Because there is an error there because of the asymptote. So we have to also consider this now because it's a tan graph. So you see, this is something that you need to include in your answer, okay? If they ask you this question and you see that denominator was tan. Okay, so in this case, how do we actually find out what x should be here so that we don't end up including this asymptote? So in this one, right, because this is the graph of y equals tan theta, this is when tan, right, we have tan 90 degrees, when the theta is equal to 90 degrees. But remember here you have 2x. So if you know that tan 90 degrees would be undefined, right? Then what exactly should x be if the function we have is tan 2x? Well, to get this to become 90 degrees, you would have to make x 45 degrees because 2 times 45 is 90. Tan 2 times 45 degrees then is going to be undefined because of that tan 90. So that's another thing we have to include here. So I'm saying this because this is a situation of tan. So you just remember that if you ever have a denominator of tan and they ask you that question, for which values of x would it be undefined, you need to include that because of the asymptote that it has there. So, or x should be equal to 45 degrees because at 45 degrees for this function, that's going to make that angle 90 degrees, and at 90 degrees we have an asymptote. So that is our answer over there. X is equal to 0 or x is equal to 45 degrees. And we move on to the next question. Okay, 5.5 says, given f of x is equal to 2 cos x minus sine squared x, we need to show that f of x can be expressed as this. So in other words, you need to get this to look like that. Okay, let's go ahead and take what we have. We have f of x is equal to 2 cos x minus sine squared x. So we have to get this to look like this. The first thing I notice is that we don't have a sine. So I know that we need to change that clearly. And what I do notice here is we don't have a sine, but we only have cos. So let's go ahead and change this sine squared x into its identity. You know that sine squared x is equal to 1 minus cos squared x. So we're going to change it to that. So we have f of x is equal to 2, and we have cos x minus, now that becomes, we need to put brackets because we have two terms. So that's 1 minus cos squared x. Okay, so f of x is equal to, and we have 2 cos x, and that distributes and becomes a -1 and becomes a positive cos squared x. Okay, it's a trinomial. Clearly it's a trinomial. We can put the one with the squared first, so it's in the order of its exponents. So cos squared x, and we have positive 2 cos x and minus 1. So can we get it to look like this? I'll think about factorizing, but remember, this is like saying k squared plus 2k minus 1, okay? If you look at k as if it's cos x. If you're trying to factorize that, you see that with the 1, you can't actually factorize because you get k and k, but then what are the factors of 1 that can give you 2? That's not going to work, okay? Factors of 1 can't give you 2 because factors of 1 is just 1 and 1. So how else? And that's already negative, okay? So 1 has to be negative, 1 has to be positive. So either way, it's going to cancel and just give you 0. So what else can we do? How else can we simplify this to get it to look like this? When we're simplifying, we try to factorize because factorization helps you to simplify expressions. But we can't factorize that using trinomials. However, you remember that if you try to factorize something and it didn't work, you would usually try using, and it was a quadratic expression specifically, right? What you would usually do is go ahead and use the quadratic formula. Now, the quadratic formula comes from somewhere, okay? It comes from actually taking a quadratic expression and completing the square on it, well, a quadratic equation, and solving for this by completing the square. So what I'm saying here is, when you complete the square on an expression, a quadratic expression, what you're actually doing is factorizing it. Let's go ahead and complete the square. Now it's going to be a bit different because, you're kind of used to completing the square on expressions that just have like x. So let's just be careful as we do that. When we complete the square in an expression, you always ensure that the coefficient of x squared is 1. And in this case, we're going to be looking at this as the coefficient of cos x, right? And it is 1. So we don't have to divide it by anything. That's fine. We don't have to take out any common factor. So we'll leave that. Then the second thing we do is we look at the coefficient of b. In this case, our b value, let me just rewrite it like this. It's kind of like having k squared plus 2k minus 1. So our b value, right, like bx, but in this case bk, our b value is 2. You would take that value, the coefficient of b, and you would half it, so divide it by 2, and then square it. And that's going to give us 2 over 2 is 1, so that's 1 squared. So we're going to use this number. Because this is an expression, we are going to take this number and add and subtract it to the expression. So this is what we're doing. We have cos squared x still, and then we have plus 2 cos x. Then we're going to take this and we're going to add it to the expression 1 plus 1 all squared, and then subtract it minus 1 all squared. And the idea behind that is we're not tampering with the value of the expression, we're just tampering with the way it looks and changing the way it looks so that we can better simplify it. And then we still have our minus 1 at the end. Okay, let me leave that in black, minus 1. And then we're factorizing. So remember, when factorizing this, when completing the square, you see that cos squared has a square. And it's always going to be the third term. This one also has a square. So what we're going to do is rewrite them into the same bracket. So put them together like that. And so we're going to have the cos of x, and we have our positive 1. Now, it's not positive because of this positive outside. It's positive because the inside one is positive. That 1 is positive, right? And then we're going to put their squared outside. The idea behind that is that if you actually take this and you factorize that trinomial, you will end up with cos x plus 1 times cos x plus 1, which gives you cos x plus 1 all squared. So we're just completing the square here. Then we still have to just simplify that. You see that's negative and we have 1 squared. 1 squared is 1, so that's just negative 1 minus 1. And if you simplify, that gives you negative 2. So you see what they actually did. That's how they got that to look like this. So the big hint was the fact that you started seeing brackets and squared. It's like they factorized here clearly, but how did they factorize? How did they simplify this further? They did so by completing the square. Okay, so that is that question. And then we move on to the next question. The next question, 5.5.2 says, hence or otherwise find the maximum value of x. Okay, so after you have actually worked through this and gotten it to this point, you need to find the maximum value of f. Now, it looks scary because it's not our usual cos graph. However, you can look at it like this. Let's think about what the cos graph looks like. Okay, the cos graph looks like this, where it kind of just does something like that and then goes back up. So something like that, right? And naturally, the graph of cos x, let's speak about that graph, y equals cos x. That graph has a maximum. The highest point it can go to is what? Is 1, okay? And the lowest point, of course, is -1. So when we have this expression of f of x is equal to, and we have all of this, all of the things that is going on here is really just what is being done to the cos graph. So just like you have a cos x plus 1, what that means is we take our original cos graph and we're going to shift it up by 1 unit, right? So that's really what is going on here. We have to look at it like that, because everything that we have going on here, the +1, the square, the -2, all of those, when applied to your cos graph, they will affect the y values of your cos graph. So I'm going to focus on specifically the maximum value. And the maximum value of y equals cos x is equal to 1. Now we're just going to go ahead and use the other things that's going on here, okay, to apply it into our cos graph and see what y value for our maximum we end up with. So this is the maximum. It was originally 1. Then what did they do to it? They took that cos graph and they moved it up by 1 unit. So it means that 1 of yours, because we're only focusing on the maximum right now. Our maximum used to be 1. We added 1 to it and it became 2. What else did they do? They took that cos x plus 1, which we've already dealt with. Our maximum is now 2. But then they took that and then they squared it. So we're going to take the number that we have now and square it, because all of these, they're affecting the y values of your graph. Okay, square that. It gives you 4. Then after they squared it, they subtracted 2. Then we're going to take that and subtract it by 2. And then that gives us 2. So it means that our new maximum is now going to be 2. Another way you could have seen this, or another way that I can think about explaining this, is you could have focused on cos x, right? And ask yourself, where does the maximum happen if we just have y is equal to cos x? What is the x value belonging to the maximum? Okay, the x value, we know that the y value is 1. The x value belonging to the maximum is 0. 0 degrees, right? What you could have done is, okay, I want to find out exactly what the maximum is. I know the maximum is not going to all of a sudden translate to something else. It's still going to be at 0 degrees, okay? Because it's still the cos graph. It's just being shifted up and down. That's really what we're seeing over here. They did not affect the x, okay? Everything has an effect on the y. It's not a cos x minus, 20 degrees, for example. So we know where it still happens. So that x value is still the same. It's still happening at 0 degrees. So you could have just taken 0 degrees and substituted into this, and you would have found your maximum. So you could have said, oh, my maximum, since I know the original cos graph, its maximum occurs at 0 degrees. I could have just said, okay, let's just say cos of 0 degrees plus 1 all squared minus 2. And if you put that on your calculator, you will indeed get 2. And there you go. See, we get 2. So there, past exam papers are extremely important to work through, because you're going to see questions that you would normally not see in a textbook. And the reason why is because they come up with new ways of asking questions. So past exam papers will really show you those new ways. Textbooks sometimes can be outdated. There are a lot of really amazing textbooks, like we've seen with the Kevin Smith textbook, we've seen with Answer series, we've seen with Mind Action series, even Platinum. There's so much helpful textbooks, but those textbooks help you to learn the content and they help you to practice. But past exam papers reflect what you're actually going to write in your exam. So it's very important to go through those. Okay, so that is it for question 5. And then we move on to question 6, which is on more trigonometry. Okay, so moving on to question 6. We are on question 6, and question 6 says, given the equation cos x minus 30 degrees plus 2 sine x is equal to 0, we need to show that the equation can be written as tan x is equal to negative root 3 over 5. Okay, so there's already a huge hint here. The fact that we have tan, but here we have cos and just sine, really just means that we need to make sure that we can somehow break this up so that we have things like cos x and sine x, because you see you have tan x here, not tan x minus 30 degrees. So we need to break that up. Okay, so this, let me just rewrite the equation that we have. And what we can do to break this one up, because we have two terms inside this bracket, we can just use the compound angle formula. So let's go ahead and expand this using the compound angle formula for cos. So that's going to be cos of our first angle, which is x, cos of the second angle, which is 30 degrees. And then because we have a minus, it changes to a plus. And then we have sine again of the first angle and sine of the second angle. Okay, then we have plus 2 sine x equals 0. And now let's see how we can simplify. Okay, so because we have things like cos 30 and sine 30, we can actually just use our special angles to simplify that. So with 30 degrees, it's not really an issue. You can actually just use your calculator. It'll be fine. So cos x, and then, so that gives us square root 3 over 2. So multiply by root 3 over 2. And then we have plus sine x multiplied by sine 30, which is a half. Okay, so multiply by a half. Then we have plus 2 sine x being equal to 0. Okay, because they are multiplying, you might as well put this as the coefficient. So we can just rewrite that as root 3 cos x over 2. Okay, so that's that root 3 over 2. And with this one, you can just say sine x times 1, which is just sine x over 2. So we're going to say sine x over 2. And then, of course, we have that over there. So we're really just trying to simplify these and then eventually form tan, okay, using that. So because they both have over 2 and we're adding here, we might as well just put them together. Actually, because we're just adding all through, let's just add all of these. So these ones are already over 2. To get this one to be over 2, you are going to have to multiply its numerator and the denominator by 2. The denominator here is a 1, okay, because it doesn't have a denominator, so it's automatically 1. And so when we are multiplying, because that is going to be over 2, and they will all be over 2, we can now rewrite it like this. It's the square root of 3 cos x plus sine x. And then when we multiply here, this is 2 times 2, which is 4. So plus 4 sine x. And remember, it is over 2 as well. So because they're all over 2 and we are adding, we can put them all under the same denominator. And this is equal to 0. Okay, so at this point, we have like terms here. Sine x plus 4 sine x are like terms, and they can become 5 sine x. So root 3 cos x plus 5 sine x over 2. Okay, I don't think we should put it together, and here's the reason why. Okay, the reason I'm saying so is because you see that here we just have a tan x. To form tan, right, tan x, we form that by saying sine x over cos x. So because I need to actually take the sine x and divide it by the cos x, it's not really helpful to have this 2 here. So what we can do is just get rid of it by multiplying both sides by 2. That's fine. And then it's gone. So now that it's gone from here, we have root 3 cos x plus 5 sine x, and then that is equal to 0. Okay, so remember, to form tan, you need to say sine over cos. So what we can do is we're going to leave sine as the subject, and then we're going to have to take that cos over. So we have 5 sine x is equal to negative now root 3 cos x. And then we can go ahead and divide both sides by cos x. So first of all, I'm dividing by cos x just so that we can form tan. Okay, so divide both sides by cos x and cos x. But you do remember that here they had just tan x. There was no number in front here. So it means that once we have formed the tan x, we shouldn't have a number in front of it as well. So because this is the sine x over cos x, that's going to be your tan x. It means that this number 5 needs to also leave. So along with dividing both sides by cos x, we'll also divide both sides by 5 so that that 5 can leave the right-hand side. Okay, so now what we will have here is the 5's cancel. Sine x over cos x gives you tan x. And then this is equal to, you see that cos x and cos x cancels here. So you have negative root 3 over 5. And that's what happens. Okay, so that's actually how they did that. That's how they made this expression look like that. Okay, moving on to the next question. 6.2 says determine the solutions of the equation, and we have cos x minus 30 degrees plus sine 2x is equal to 0. Okay, so it's still the same equation they're referring to, but we just need to actually solve for x in these intervals. Okay, so let's go ahead and find that. It's really like general solution. Because we've already simplified this equation that we had here to this, we can just work on that. So we're really just trying to find, first of all, the general solution or this equation, and then we're going to go ahead and find those specific x values within this interval. Okay, so let's go ahead. We have tan x being equal to negative root 3 over 5. Okay, and at this point, I think I'm actually glad that this came in, and the reason I'm saying so is because, like I explained in this paper, right? In this particular video, actually, because we worked on question 5 that had a tan x situation. It was tan 2x. Remember when I said that when the value, right, of tan x or tan whatever angle you have is negative, once you get your answer will be a negative angle. If you wanted to make it positive, remember I said you need to add 180 degrees, not 360 degrees. The video that I'm showing now, I said add 360. It's not 360 for tan. It's 360 only for sine and for cos. Okay, so let's go ahead and work on this. So what we're going to do is go ahead and find our reference angle. I am using the quick method here. You can go ahead and use the standard method, and you can refer back to that video to see how to use the standard method there. So we have our reference angle is equal to, and so to find the reference angle, we say shift tan of this that we have, negative, and this is a square root 3 over 5. Okay, so let's see. We get negative 19.11 degrees rounded off to 2 decimals. And I will round off to 2 decimals. It's not a problem because do you see that we're just trying to solve for x, not 2x or 3x or half x? Because we don't have to divide at the end. It's fine if you round off to 2 decimal places at this point. So this is our answer that we have for the reference angle. And then remember to solve for x with tan. It's very simple. All you just say is x is equal to whatever your reference angle is, then plus k, 180 degrees, where k is an element of integers. That's all. So to solve for x here, we just say x is equal to, our reference angle is negative 19.11 degrees plus k of 180 degrees, where k is an element of integers. Okay, so now we have to find those specific solutions. With the specific solutions, I like to use a number line just because it's neat and it's more ordered. It's easier to find your answers in a way that is already structured so that you don't miss anything. So the number line, the numbers that we're using here, remember that k is an element of integers. So we're only going to be using integer values and substituting it into this expression. So we can go ahead and start from 0. I always start from 0. If you substitute 0 into this, what do we get? You see that if we substitute 0, we get the same thing that we have already, okay? So I just said 180 and then that's k, okay? we get the same thing. So you're going to have to think about this now. Negative 19.11 degrees. Is that within the interval that we have? Well, yes. Okay. From negative 180 to 180. So we can accept that answer. Then after trying 0 as an integer, we can go ahead and try negative 1. So I go from here, then to the left. So let's try negative 1. So if we substitute negative 1 into this, let's see what we get. We get negative 199.11. Do you see that that's just way too far? Okay, it's way too far, so I'm not even going to try using it. We can go ahead and say that negative 1 did not work. And that means you don't have to try negative 2 because it definitely will not work. Then we can go ahead and try 1 as an integer value. So if you substitute 1 there, you get 160.89. So that actually works out. You can go 160.89 degrees. That works. And it's already way too big. 2 will definitely not work. Okay, see, way beyond that. So we don't have to try that. So these will be our answers. We can go ahead and tell them. Therefore, x is equal to negative 19.11 degrees, or x is equal to 160.89 degrees. If you had used the standard method with the diagram, you would still get the same answers because you have to move within intervals of 180 degrees. So you're just moving through like that. That's why we substitute integer values. The only difference is your answer would have been positive. So if we wanted to get that same answer, you could have just added 180 degrees to this and you'll see that it will be the exact same thing. Okay, lovely. We're done with that question and moving on to the next question. Okay, so we're on 6.3 and it says, in the diagram below, the graph of f of x is equal to negative 2 sine x is drawn for this interval where x is an element of negative 150 all the way to 210 degrees. Okay, the first question is write down the amplitude of f. Okay, so we're looking at the graph of f. And from the equation already, you can see the amplitude. Yes, we have a negative 2 over here. You just have to take the absolute value of whatever is here. So if it's negative 2, you're just going to take 2 because the amplitude is really just speaking about the height of the graph from the midline. So this would serve as the middle of the graph, right? The vertical middle. And so the height is 2 units. So we can go ahead and tell them that the amplitude is 2. Then the next question, 6.3.2 says, draw the graph of g of x is equal to cos x minus 30 degrees for the interval where x is an element of negative 150 to 210 degrees on the grid provided in the answer book. Clearly show all intercepts with the axes and the endpoints of the graph. Okay, so look at the graph we're drawing. It is g of x equals cos x minus 30 degrees. So do you see that the only thing that happened here, okay, from the original cos graph, cos x, is that we just have a minus 30. So we're subtracting from the x. When you subtract from the x, or when you affect the x, what you're really doing there is this is a shift. So it's a horizontal shift. It's either to the left or the right. If it is a minus, it's moving to the right. If it's a plus, it's moving to the left. Remember that this only works when we are subtracting or adding to the x. Okay, if it's on the outside, then it's a y, and plus would be up and minus would be down. Okay, so that's what we have to think about. So what we can do here is think about what the original function of cos looks like. And then based on that, we can actually draw what this cos graph would look like. So the normal cos graph, and I'll just draw a little diagram of it so that you can see what I'm working off of. The normal cos graph, right, looks like this. Okay. And it's really like a zigzag pattern, but it's just curved. So at 0 degrees, just remember that at 0 degrees, we would have 1. Okay. And then at 90 degrees, so you'll notice there will be a difference, or there will be an important point every 90 degrees. Okay. So after 0 degrees, 90 degrees later, your cos graph is going to have a y value of 0, so it's going to be on the x-axis. And then 90 degrees later from that, that is 180 degrees, your cos graph will have a value of negative 1. And then after that, 90 degrees later, at 270 degrees, you're going to have a y value of 0. And then 90 degrees later, at 360 degrees, you would have a value of 1. And that's why that cos graph ends up looking like that. Okay. So what we're going to do is think about how it's going to look in our diagram since this graph has been shifted 30 degrees to the right. Okay, so everything that we had here is now going to move 30 degrees to the right. So in this one, the reason I'm going to just continue it is just so that you remember what it's going to look like, since we do have, values beyond 0. We have negative values as well. So let me just go ahead and take this line and extend it. If we extend that line, trying to grab the line specifically. So if we extend that line, what's going to happen here is, you see the way this graph looks, it's going to take on the same form on that side as well. So it'll also do that like that. Okay, and really just does the same thing. So from 0 degrees, 90 degrees later at negative 90, it's going to be at 0. 90 degrees later, okay, it's at negative 180, it will be at negative 1, and so on. So how we can actually draw this graph down is based on that. Since we know that it's going to move 30 degrees to the right, every time we have a value, we're just going to keep moving that angle 30 degrees to the right. So this is what I mean by that. You see by negative 180, right? We should have had a y value of negative 1. Instead, this y value of negative 1 will not appear at negative 180. It will appear at negative 150 degrees because the cos graph is being shifted 30 degrees to the right. So it should have been at negative 180, but because it moves 30 degrees to the right, it's going to now appear at negative 150. So that's where that y value of negative 1 will be. So that, and that's probably what they meant by the endpoints. So that, and then the next one, so we're done with the 180. The next one is that 90, negative 90, right? At negative 90, you see that you have a y value of 0. So what's going to happen here is at negative 90, we're not going to have a y value of 0 anymore. This is going to happen 30 degrees later, okay? 30 degrees to the right. So that's going to be at negative 60 degrees, right? Negative 60. Then here at 0 degrees, where we were supposed to have a y value of 1, it will not happen at 0 degrees anymore. It will happen at 30 degrees to the right of this, which is at 30. So now that's where you have 1. Okay, we're done with the 0. And then the 90 degrees was supposed to have a y value of 0. Instead, we are going to have this not happening at 90, but at 120. That's where you have your 0. And then at 180, you should have had a y value of negative 1. A y value of negative 1 will not happen at 180 anymore. It will happen 30 degrees later, which is at 210 degrees. Okay, so that's where you're going to have that. And then you're just going to draw your graph. So it's just a curve. So you're just going to connect them and make sure that it curves. Okay, so something like that. So that is our graph of G. We'll just label it G. And we know that this one is the graph of F. Okay, so there we have joined that graph. Okay, so the reason I did this and I didn't go ahead and just draw the cos graph and then move it to the right is because in an exam setting, that is not really what you would be able to do. So I just decided to explain it in a similar way that it would have been done if you were working on it in an exam. Okay, so that is that. We're done with that question and moving on to the next question. The next question, 6.3.3 says, use the graphs to determine the values of x in the interval where x is an element of negative 150 to 210 degrees. So it's still the same graph in that same interval for which g of x is greater than f of x. Okay, remember that these are referring to the y values. Okay, when you're looking at two graphs and you're concentrating on their y values appear on the y-axis. So if you have a graph like this and you have another graph like that, and we are looking at the y values of this graph, just remember it is for that same x value. Okay, so let's say this graph's name was f and this, well, let's just call it g, and this was f. Then if I'm asking for places where g of x is greater than f of x, I'm really just asking for places where the graph of g has a higher y value than the graph of f. So in a nutshell, what you're going to be looking for is the places where the graph of g lies above the graph of f. So that's the whole point behind that. So that's what we're going to do. Look for places where g is higher than f. Okay, so let's go ahead and see. So we have G and we have F. We need to look for places where G is higher than F. So as you can see, all through here, it's not working because G is below F. But then something happens at this point. They first intersect, right? And remember that when they intersect, they are exactly equal to each other. Then the graph of G is now higher than the graph of F. So this is where it's greater. And then they intersect again, and then the graph of G goes below the graph of F. So this is really what we're trying to focus on, this area over here. We're trying to find out what exactly are the X values for the graph over here. Okay, so let's find that. Do you see that two very important points here would be their points of intersection? Because if we knew exactly what number this was, and we knew exactly what number that was, we'd be able to see that the graph of G is greater than the graph of F for places that are greater than whatever that number is, but less than whatever this number is. All through there, so all through these numbers here, that's where the graph of G lies above the graph of F. So we're going to have to find their points of intersection. In other words, what we're trying to find out is where is G of X equal to F of X. Okay, so let's look at what those two graphs look like. We know F of X is negative 2 sine X and G of X is that. Okay, so we're trying to see where is G of X equal to F of X. That is cos X minus 30 degrees. Where is it equal to negative 2 sine X? And now I see that this looks familiar. This is the first question. Okay, so they continue in this. Do you remember that here in this question, we actually dealt with this already? We dealt with it here. They started off this question by giving us this equation. Do you recognize this now? They gave us this equation and they said that we had to basically simplify it, show them that it can be written like this. Now, the reason I'm saying it's the exact same thing is because do you remember that G of X is this cos X minus 30? But we have a plus here. We have a plus 2 sine X. If you take that over, what does it become? It becomes negative 2 sine X. So really, this is the equation that we just solved for already. We solved for X for where cos X minus 30 degrees was equal to negative 2 sine X. And we already know the solution to that. The solution to this is these two, okay, between this interval that they gave us. But if we think about that, look at those solutions that we have, negative 19.11 degrees and 160.89 degrees. Does that work for our interval? Is that actually solutions we can accept for our interval? Well, yes, because do you see, look at the interval that we have, negative 150 all the way to 210. That is within that interval. See, that is like greater than negative 150. And this is also within that interval. You can find these numbers in here. So that means we can accept these. These are the points of intersection of those two graphs. So now we don't have to guess anymore. We know exactly what those values are. So we're going to put that there. That's negative 19.11 degrees. And this one over here is that 160.89 degrees. Okay, so in a nutshell, the places or the values of X for which G of X will lie above the graph of F or be greater than the graph of F is where X is greater than all the values that are greater than negative 19.11 degrees, but smaller than 160.89 degrees, because you see it's all the values in between negative 19.11 and 160.89. So that would be our answer over there. Okay, so that is the answer to that question. And then we move on to the next question. Then the next question B, we need to solve for X, or really find the values of X within that interval for which f prime of 1 over 2x is equal to 0. Okay, so this is only for 1 mark. So it means it's a simple question. Let's understand what f prime means. If the question was f prime of x is equal to 0, you had to give them the values of x for which f prime of x is equal to 0. Let's think about what that would mean. So the graph of f is that sine graph, right? The black graph over there. where f prime of x is equal to 0, f prime, you use f prime when you're trying to find the gradient of a curve. When you're trying to find the gradient. So it means this is where the gradient is equal to 0. You're going to have to think about that. In a curve, where's your gradient equal to 0? That happens at your turning points. The idea behind that is that a curve, right? It's made up of points that are increasing and points that are decreasing. But at the turning point, this is the point where it neither increases or decreases. It just stands still. That's why we call it a stationary point. Okay, so at this point, this is where our gradient is equal to 0. At these points, our gradient will be positive because do you see that this is increasing? You always read graphs from the left going to the right. Okay, here it's positive, here it's negative, and here it's equal to 0. So that's what we're looking for. We're looking for where the places where the graph has a gradient of 0, right? So if this was the question, our answer would be very simple to be, okay, we're trying to look for places where it curves. And you'd have to look for the turning points of this graph. Just like a parabola, the turning point happens at that point that we're turning, right? Here and here. Now, they're not just random places we're picking. We know the point that it starts to turn. Because it's a sine graph, it's really just that maximum and the minimum point. The maximum of a sine graph, because this graph hasn't been shifted to the left or the right, that maximum happens at negative 90 degrees. So that's how we know that is negative 90 degrees. And this one we know is 90 degrees. Okay, that's where the minimum happens. So that's the maximum and that's the minimum turning points, really. Okay, so we would know this answer. If the question was this, our answer would be very simple. It's x is equal to negative 90 degrees or x is equal to 90 degrees. Very simple. But the question here is a little different. It says f prime of 1 over 2x. So we're going to have to understand what exactly it means to put a coefficient in front of x. What does that mean? Well, this is a concept that you guys have already worked on in trigonometry, specifically in trig graphs. You see that if you have a graph y equals sine x, the minute you put a number in front of x, what does it do to the graph? It changes the period of the graph. So, like a sine graph, right? It usually takes 360 degrees to complete one cycle. But the minute you put a 2 here, right? What is going to happen is that it makes your graph more narrower. So instead of it completing a cycle in 360 degrees, it would complete it in half the amount of degrees, really. It's going to complete the cycle in 180 degrees. Now, I know I just said that, but I want to show you how you would calculate that. How would you find out how fast is it going to complete a cycle? You find out by taking the old period and you divide it by that coefficient of x. So in this situation, the reason I know it completes a cycle in 180 degrees is because the old period of a sine graph is 360 degrees, but we know that the coefficient is 2. So that's why we know that the new period would be 180 degrees, and that's what makes the graph more narrow. Okay, so now that you understand the idea behind that, what happens when we put a half here? What's going to happen there? Okay, so we know that the normal sine graph completes a cycle in 360 degrees. What's going to happen with this one? Well, you can say 360 degrees divided by a half. What does that give you? Gives you 720 degrees. So this is going to take much longer to complete a cycle. Instead of it completing it in 360 degrees, it's going to take double that amount of degrees to actually complete. So what's going to happen is that this graph is actually going to get much wider like that. And the thing about it is, just like what happened with the period, you see that what happened with the period is that the period ended up doubling, right? So if the period doubles, so does every other x value that you had. The normal sine graph, and I think I should just put 2 of them here. I should really just copy this and then put it here again. So here is the one that completes in 720. right? So when we're looking at the normal sine graph, you know that I'm going to focus on the important points that we are referring to here. You knew that if you were just looking for f prime of x, like I showed you here, you knew that this was going to happen at negative 90 and positive 90, of course, right? So I'm saying that here we have a maximum turning point at 90 degrees. Well, if the period of this graph has been changed, because that's what happened to f prime 1 over 2x, they put a 1 over 2 in front of the x. What's going to happen now to that maximum? Where will it appear? It would appear in double of 90 degrees, because that's really what these angles are doing. The solutions that you used to have for this graph are going to happen in double the size of whatever angle they're at. So that maximum will not happen at 90 degrees anymore. It will happen at 180 degrees. Okay, so we know that now. So with our graph, when we're looking at the graph, because the maximum and the minimum used to be here and here, where are they going to be now? This one that was at negative 90 will happen at negative 180 degrees. And this one that was at 90 is going to happen at 180 degrees, positive 180. So our solution for that, where is f prime of 1 over 2x equal to 0, right? Where is the gradient of this graph that has been altered equal to 0? It's going to happen where x is equal to negative 180 degrees, or where x is equal to positive 180 degrees. Okay, I hope you guys understood that. Please do comment in the comment section if you still have questions on it. Okay, so that is it for question 6. That's not the end of this video though, because we still have 2 and 3D trigonometry in question 7. So moving on to question 7. We are on the last question for the trigonometry part of this paper, and that's question 7. Question 7 says, in the diagram below, P, Q, and T are 3 points on the same horizontal plane. Okay, that's P, Q, and T. Okay, so they are on the ground. You can actually look at it like that. That's the floor of this diagram. Then they tell us that an MT is a vertical mast. So we have that over there, which is just a vertical line that we have. And then MP and MQ, MP and MQ. So these two, right? That those are two straight stay wires. And then the angle of elevation of M from Q is theta. So the angle of elevation of M, okay, from Q. So that angle that they're measuring over there. Lastly, PQ is equal to K meters and PM is equal to 2 times PQ. Okay, so that's simple. If PQ is K and PM is 2 PQ, so it's 2 times the size of PQ, meaning this is 2K. Okay, so we just put that down already so we know. And then they tell us that the area of triangle MPQ is this. So MPQ, this triangle over here. So this front part, the flat side here. So we have the area of that. Okay, first question. 7.1 says, show that MPQ is equal to 2 theta. So we need to find the angle MPQ, this angle over here. Okay, they just told us something about this triangle, okay, that this angle belongs to. This triangle MPQ, we have the area of it. So we can probably use that. Since we already have the area of this triangle, let's just see how they would have calculated the area of it. Well, as you can see, there is no perpendicular height here, so we can't really use that area half times the base times the perpendicular height. We can't really use this. So we can use the other area that we know. So I'm focusing on this triangle, right? So we're saying the area of triangle, so area of triangle MPQ, that's also what they called it, that to calculate this, the formula we would use is say a half. So I'm saying a half multiplied by the side next to the angle that is our focus angle. So a half times PQ, which we can see is K, right? Multiplied by PM, which we can see is 2K. And then we're going to say, so multiply by 2k. And then you're going to say sine of that center angle. So sine of angle MPQ, because we don't really have it right now. So sine angle MPQ. So this is the area formula. Okay, area of a triangle if you don't have a perpendicular height. But the good thing is that we have the area already. They told us the area is this. So I'm going to put that down. 2k squared sine theta cos theta. That's 2k squared sine theta cos theta. And then we still have this, but we can just simplify a bit. So you see that we have a half times, we have a 2 there, right? And then multiplying all through. If you say a half times 2, what happens is you have a 2 over 1 here, and your 2's will cancel diagonally. So they really just give you 1. Okay, so you can really say those cancel, they become 1, and they multiply in here, and they just really leave that the same. So we have k times k, which gives us k squared. And then we also have still our sine of angle MPQ. Okay, so this is what we have, and we're trying to find this angle. Because we're trying to find this angle, we just have to make this the subject first of all. So if we can make that the subject of the equation, we can then go into finding that. So to make that the subject of the equation, we have to get rid of the k squared because it's the only thing in the way right now. So we'll divide both sides by k squared since k squared is multiplying to sine angle MPQ. And let's go ahead and tell them that sine angle MPQ is equal to, and we're going to rewrite what we have here. But do you see that they're going to simplify? Since you have a k squared and a k squared, they cancel. And all we'll be left with is 2 sine theta cos theta. Okay, the goal is to still get angle MPQ. Now, the thing is, because this is sine of an angle, you can take sine over. And when you take sine over, it becomes the inverse of the sine function, okay, which we see as shift sine. And what shift sine does is that it will cancel out a sine. But then what are we going to do with the cos? And it doesn't really look right to do that because we have to say shift sine of this whole thing here. So when you look at that and look at the answer for MPQ, it doesn't include any cos or anything like that. So because it doesn't include that, clearly this cos has to go. Okay, so how can we actually get that cos to leave? Okay, do you see now that this is actually an expansion of one of the double angle formulas? The double angle formula that says sine 2a, if you expand it, it gives you 2 sine a cos a. So do you see that this would simplify to sine 2 theta? Okay, just like with that. So because it simplifies to sine 2 theta, we still have this over here, sine MPQ. And now we can go ahead and take sine over. So when sine goes over, what actually happens, or you're going to really just see it as what we're doing on both sides is we are using the inverse of sine on both sides, okay? But I like to take things over. So what happens there is you're going to have the inverse of sine with the sine function. And because they're the inverse of each other, they would actually cancel each other out. And therefore, MPQ, that angle, is equal to just 2 theta. And that's how we get that. Okay, so that is the first question. That was 3 marks. Moving on to the next question. The next question, 7.2 says, hence, show that MQ is equal to K 1 plus 8 sine squared theta. Okay, so we're really just trying to solve for MQ and ensure that it looks like that. So let's actually fill in our diagram. Since we already found out that this is 2 theta, let's fill that in over there. So we know now this one over here is 2 theta. This is what we have so long, and we need to find MQ. So if you're trying to find MQ, what rule can we actually use to find this? So I can't really use this triangle over here because there's not much information. All you have is theta inside there. So we're not even going to bother trying to use that triangle. How about we use this triangle? But do you see which trigonometric formula you can actually use here? The trig formula you can use here, because we do not have MQ, is the cos formula, the cos rule. Okay. So because this is the side we're looking for, right, that we're going to say mq squared is equal to, and then we're going to say the side next to it squared, that's pq squared, plus the other side next to it, which is pm squared, then minus 2 multiplied by the pq multiplied by the mp or pm, as I called it there, and then you're going to say cos of that center angle, which is that mpq. Okay, but the main focus is really just getting these letters and these variables. So MQ is what we're looking for. We actually don't have that one, so we'll leave that as MQ. But as for PQ we have is K. That is K. So that's going to be K squared plus, and then PM. PM is 2K, so that's 2K that gets squared. And then minus 2 multiplied by the PQ, we know that that is K, multiplied by the PM, we know that is 2K, and then cos of that center angle, which is 2 theta. Okay, and I'm just going to go ahead and write this down. So there this is. And all we're trying to do is solve for MQ. Okay, so to solve for MQ, we're going to go ahead and say MQ squared is equal to, and we have K squared, and then that's going to become, the 2 squared gives you positive 4, and then we have K squared. Then when we multiply through here, you see that you have a negative 2, and then along the line, you also have a positive 2. So they multiply and give you negative 4. Then K times K is K squared, and then cos of 2 theta. Okay, so at this point, we're still looking for MQ, right? Because this is squared, we can go ahead and try to solve for MQ by getting rid of the squared. So you do that by square rooting, but this is an equation, so you have to square root both sides. Okay, so this means that MQ is equal to, and let's just say square root and simplify what is under the radical. So K squared plus 4K squared gives you 5K squared, and then you still have the minus 4K squared cos 2 theta. So remember what this looked like. That's a sine. So we're just going to have to simplify as far as possible. So with this MQ equals, well, do you see that under the radical you have 2 terms? This is the first term and the second term. And do you notice that in these 2 terms, we have K squared that is common. So we can actually take K squared out as a common factor and then open a bracket. What is left in the first term when you take K squared out? It's like, say, this divided by the K squared. And that gives you 5. And then this divided by the K squared cancels, and only negative 4 cos 2 theta would be left. Okay, the good thing about this is, you see you have a K squared and then you have brackets protecting what is inside here. Because of that, the K squared can actually get square rooted. The idea behind this is, if you had, for example, let's say the square root of 4 multiplied by 2, because they're multiplying, you can actually split them up like this. This is actually the square root of 4 multiplied by the square root of 2. And the square root of 4 can get simplified to 2, and the square root of 2 can't, so it will stay square root 2. Okay, so that's the idea behind that. So that's what happens there. It gets square rooted, and we're going to have MQ being equal to K, and this does not get square rooted. Unfortunately, it can't, because you have a minus here. You cannot square root through a minus sign, so that stays, and then we have 5 minus 4 cos 2 theta. So where does this sign come from? Where does that come from? Well, they probably changed this 2 cos theta to one of the double angles expansion for cos 2 theta, but one that only has sine. Let's think about the one that only has sine. That would be, okay, the cos 2a, that would be the one that says 1 minus 2 sine squared a. That would be that one. That's the only one that only has sine and no cos included. So it means we're going to change it to that. So we're actually just saying that to solve for MQ, we say MQ equals, and we'll say K square root of 5 minus 4, and we're going to change this. So remember, it changes to something that has 2 terms. So you need to protect it with brackets. So that changes to 1 minus 2 sine squared of theta. Okay, so that is what we have there. Then we're going to simplify further. So MQ MQ equals K square root of 5, and then we distribute. So that's going to give you -4, and then that's going to give you positive. And then you see it's -4 multiplied by -2, which gives you positive 8 sine squared theta. And as you can see, we're basically done at this point. MQ is equal to K square root. And over here, because these have now been separated into terms, 5 minus 4 is 1 plus 8 sine squared theta. And that is exactly what they did. So always make sure you look at their solution, their answer, and just see how can you actually get yours to look like theirs. Okay, so that is what we have there. That's the second question in question 7. And then we move on to the last question in question 7. So the next question says, if K equals 139.5 meters and theta is equal to 42 degrees, determine the length of MT correct to the nearest meter. Okay, so no decimals, so just correct to the nearest meter. Let's go ahead and see how we can actually find MT. Remember, always use what you previously got. So we're going to have to fill that in. We have MQ now in our diagram. So I have all of these things that we've already filled in and MQ. MQ is that number that they gave us. So that K square root 1 plus 8 sine squared theta. So that's what we have there. Now, how can we actually use this to find MT? Well, you see that we have a right angle triangle here. See, we have a right angle triangle. So you can use trig functions on it like sine, cos, and tan, okay? So with this, we have a reference angle theta. And let's just see how we can actually use this to find MT. Always focus on this when you're trying to work with trig functions, okay? When you have a right angle triangle, you ask yourself, what do I have and what do they ask me to find? What we have is this. We have MQ, which is our hypotenuse. So we have H. What they asked us to find is MT. So you're going to have to look at that in reference to the angle that we have present here. They asked us to find MT, which is clearly the opposite side. So you see that you're working with the opposite side and the hypotenuse. So which function are you going to use? You're going to use sine. So we're going to use sine and go ahead and tell them that sine of our reference angle was theta is equal to the opposite side, which you saw was MT, over the hypotenuse, which is this whole thing, this MQ. But I'll just write the expression that we have there. So that is MT over MQ, which is that K square root 1 plus 8 sine squared theta. So all we have to do here is make MT the subject and then substitute these values. Okay, to make MT the subject, we can just cross multiply. So here the denominator we have is 1. 1 times MT stays MT, and then sine theta times all of that. I'll just leave the K in front. So it's K sine theta square root 1 plus 8 sine squared theta. So that's what happens because this is under the square root. It can't multiply with that one. Okay, so this is what we have, and we're just going to substitute. So finally, let me just put it like this. MT is equal to, we know what K is now. K is 139.5 meters. And we have sine theta is 42 degrees. And then we have square root of 1 plus 8 sine squared of 42 degrees. And you're just going to substitute that into your calculator and find out what exactly MT is, rounded off to the nearest meter. Okay, so just remember on your calculator, when you're putting that sine squared, you can't go sine and then squared. It's not going to work. You have to say sine 42 squared. So the answer that we get there, right, the number that we get is that 199.80. But they said round off to the nearest meter, meaning to the nearest whole number. Okay, so this is going to be approximately 200 meters. And that is the length of MT. Okay, so that is it for the trigonometry section of this paper, and I will see you guys in Euclidean geometry. All the best for prelims and keep practicing, guys. I'll see you guys in the next video.